Okay, welcome back, covalent bonding. So the next part of this work is to think about shapes of molecules. So now we have Lewis structures, we kind of understand about covalent bonding and that it's a sharing of electrons. We know about Lewis structures, how to connect atoms and draw them using the octet rule. And now we need to progress to predicting the shapes of molecules. And I think we'll make clear in class the importance of this, but in general, being able to predict the shape of a molecule is really useful for kind of making some predictions about how it's going to behave. And this is particularly true in medicine and biology. So there's a lot of sort of structure or shape function relationships in biology. So for example, you may have heard of an enzyme that has a receptor, and the receptor will be a very specific shape, and only certain molecules can fit in there, and that has to do with their shape. So it really does matter what these molecules look like, how they're built, and the shape of them. Well, that's what we're going to study now. So molecular shape. All right, so the Lewis structure that we just studied gives us information about how the atoms are connected, but it doesn't really tell us anything about the shape. So to determine the shape, what we're going to do is draw that Lewis structure because it's a useful tool, and then we're going to count groups, electron groups around the central atom. So we kind of zoom into the central atom and we're going to count electron groups. And then, a group can be considered either an atom or a lone pair. Okay, so an atom or a lone pair. That'll be the way that we think about these groups. And what we're going to use to make the prediction is something called VSEPR theory. And this stands for valence shell electron pair repulsion theory. So it's got a long name, but basically it's this idea that you can make a prediction about the shape around a central atom. And so you can actually look at big molecules with this theory too, and we'll try to do that in a little bit. The VSEPR theory or VSEPR theory tells us that the most stable arrangement keeps the groups, so whether they're atoms or electron pairs, as far away from each other as possible. So in other words, in three-dimensional space, these groups are going to get as far away from one another as possible. It's really nice to explore the molecular shapes with molecular models, and so we will do that in class, but hopefully you can get the basics down before you come to class. All right, so let's take a look at what this is. So any atom surrounded by only two groups, so in this case we have a kind of a fictitious molecule shown here with the central atom being the red ball here, and then the two outside atoms, the blue balls. Okay, so if we were to count groups in this case, we have one group and then two groups. We've got two groups, and that is always going to give rise to what we call have a linear shape. In other words, the bond angle of 180 degrees, because those two groups want to get as far apart from each other as possible. So that's why they're at 180 degrees from one another, and we call that linear. So you might be asked a couple of questions. You might be asked to first draw the Lewis structure and then predict the shape. And in order to predict the shape, you would be noting down the bond angle and what the name of the shape is. So linear and 180 degrees in this case. Let's look at CO2 as a specific example. Now, if we were to draw the Lewis structure of CO2, we would have this structure as shown down here. So it'd take me a little time to show you how to do that, but hopefully you can go back, use your Lewis structure drawing skills to draw that molecule or draw that Lewis structure and show that. So basically, we've only got two atoms connected to carbon, right? So we've got two oxygens. So that's two groups connected. And we're going to then be able, so that's the same as the fictitious example above. We basically have two groups, so they're going to be 180 degrees apart from one another. And we say that CO2 is a linear molecule with a 180 degree bond angle. So that's how we would say that. And just as a warning, this last note here, we're going to ignore multiple bonds in predicting geometry or predicting shapes. You count only the atoms and lone pairs around the central atom to sort of count your groups. So it's all about groups, counting up groups in this case. Okay, let's look at another example. And our fictitious example is when we have three things around a central atom. So notice this molecule here, it's fictitious. It has three groups, so 1, We can just go around 1, 2, 3 groups. And we call this trigonal planar. So this has a trigonal planar, and these groups are 120 degrees from one another. So you can kind of see that. And if you had a model, you'd be able to see that that's as far apart as they can get from one another. And that's what VSEPR theory, VSEPR theory tells us. Those groups are going to get as far apart from one another as possible. And if we look at a specific example, we've got formaldehyde that has this Lewis structure as shown down here. We've got a carbon as our central atom again, double bonded to an oxygen, and then the 2 hydrogens off of the carbon as well. So again, we have the 1, 2, 3 groups around carbon, and that corresponds to a trigonal planar molecule with a 120 degree bond angle. All right, so that's a second example. Let's look at a third example. So in this case, we have 4 groups, so we can just count 1, 2, 3, 4. So that's what you'll be doing as a first step is, well, you might need to draw the Lewis structure, but then you count the groups, and once you have the groups, then you can correlate that with a name for the shape and a bond angle. It turns out when you have 4 groups around a central atom, they are going to be 109.5 degrees away from one another. That's as far apart in space as they can get. And again, in lab, you'll be able to see that. We'll build some of these, and you'll be able to see that angle nicely. So we refer to this shape when there's 4, when there's 4, atoms around, as tetrahedral. So this is a tetrahedral with a 109.5 degree angle. And we can look at methane as our example. So again, if you drew the Lewis structure, you'd have this structure you see down here. And there's, again, 1, 2, 3, 4 groups around carbon. And so that's what we mean when we say we have a tetrahedral shape with a 109.5 degree angle. Okay. So if 4 groups around the atom include 1 lone pair, the geometry is called trigonal pyramid, or pyramidal is the way I like to say it, but trigonal pyramid with bond angles of 107 degrees. So let's look at an example. Ammonia is an example. So if we're going to count groups here, we're going to count this lone pair of electrons on ammonia in H3. That's 1, 2, 3, 4. So similar to the methane molecule we just saw on the last slide, this has 4 groups. And so the angles should be right around 109.5, because remember that the 4 groups were 109.5 degrees apart. But in this case, because we have this lone pair of electrons here, it does count as a group, but it takes up a little more space. So it's kind of pushing down on these bonds just a little bit, shrinking these angles. So because we're interested in the angles between the central atom and the actual atoms, the outside atoms, we're going to say that those angles are decreased a little bit. In this case, it's about 107 degrees. So anytime you have a lone pair of electrons on the central atom, you're actually shrinking down those bond angles just a bit. Okay, so that's ammonia. And so we say it's got a trigonal pyramidal. There's our pyramidal molecule with a 107 degree bond angle. Okay, and here's another example where we have 2 lone pairs. Water is a great example of this. Again, if we go down and look at the Lewis structure of water, we've got 1, 2, 3, 4 groups. So if you remember, that should be right close to 109.5, because if you had all atoms attached, it would be 109.5, because that goes along with having 4 groups. But in this case, we have 2 lone pairs of electrons, and they, again, are pushing down. If you see it in this next drawing over here, they are pushing down, taking up a little more space, really shrinking down this angle here. So those are taking up a little more space. You can kind of think of them as these big clouds, and they're pushing down on these bonds, shrinking this angle. And it turns out it's right around 105 degrees for water. And that's because there's 2 lone pairs as opposed to ammonia in the last example, which just had the 1 lone pair. Okay, so those are, some examples, and we can kind of summarize this idea all in a chart that's in your book. So I highly recommend that you check this out and become familiar with this chart. But basically, we went through this already. If we've got, number of groups is 2, then notice that we've got the linear shape with 180 degree bond angles. And here's a couple of examples if you want to draw those out. And then we saw an example when you have 3 total groups, and that gives us our trigonal planar with a 120-degree bond angle. So again, we saw that example, and that's always going to be the case. And then we had 3 examples in this category where there were 4 total groups. And in one case, we had 4 atoms and 0 lone pairs. So we saw that, and that was kind of an ideal geometry. It's got a 109.5-degree bond angle, and we call it tetrahedral. And then also with 4 groups, we saw another example where there were 3 atoms attached in 1 lone pair. We called that trigonal pyramidal with something less than 109.5. And again, you wouldn't have to know exactly what this angle is, but saying less than or approximately or close to is actually an okay thing to do. So if you see that lone pair and on there, you know that the bond angles just are shrunk just a little bit from that ideal geometry or that ideal bond angle. Again, we also saw 4 electron groups, and this gave rise to a bent structure. We had the 2 bonding and 2 lone pairs. So here we have those 2 lone pairs, again, pushing down, shrinking that angle to less than 109.5. Okay, so this chart is in your book. I highly recommend that you spend some time with it. You use it to practice with. We will build molecules in lab, and you'll have more time to kind of practice this skill. All right, let's just try to do a couple of examples in the next couple of minutes here. So first we would need to draw the Lewis structure for this, which I'm going to do kind of quickly, but remember all your Lewis structure rules to get this drawn quickly. Okay, there we have our Lewis structure, and we're going to count groups. So 1, 2, 3, 4 groups. So we have 4 groups. Anybody remember what that would be called in terms of a name for the shape? And if you've forgotten, we can just go back. Oops, wrong way. Sorry. Go back to our chart. We're right here where we have 4 atoms and 0 lone pairs. So yes, it was tetrahedral and 109.5. So let's just write that out. So this is what you'd be asked to do. And in fact, you'll be asked to do that in a lab. All right, here's another one. C, Cl, Cl. Looks like I need to actually use multiple bonds, so I'd love to take away one of those lone pairs, get rid of that one, not a lone pair, and we'll put a bond there. So here we have 1, 2, 3 groups, and if you recall, this would be, there's no lone pairs, we would have trigonal planar. Anybody remember the bond angle? That's right, it was 120 degrees. Okay, last one, PF3. Oops. Let me write this out. Okay, so it looks like we've got, if you draw the whole Lewis structure, we're going to have a lone pair on here. So we've got 1, 2, 3, and 4 groups. But we have 4 groups with a lone pair. Let's go back quickly. So we have 4 groups right here with 3 atoms and 1 lone pair, so it's trigonal pyramidal and a less than 109.5. So trigonal pyramid's fine too. Less than 109.5 would be fine. Okay, so that's how you use VSEPR theory to predict the shapes of molecules. Be sure to use that chart. I think it's extremely useful. And lastly, I'd just like to say a few words about biomolecules. It turns out that once you know VSEPR theory, you can predict the shapes of molecules, of even very large molecules. We have this big triglyceride, a big fat molecule, and we could take it one central atom at a time and predict the structure. And we're going to do that in class a little bit, but notice this carbon right here has 2 hydrogens attached to it and 2 carbons. This here, and then it's got these 2 hydrogens coming off here. So that's 4 groups with no lone pairs. Anybody remember? That's right, it's tetrahedral. So you could literally go through every one of these central atoms. Just take it, multiple central atoms. You could take each one at a time and predict the shape around it. And in fact, we have computers that do this for us. So we don't spend a lot of time taking it each atom at a time, each central atom at a time. But we're going to actually do some of that prediction and that kind of work in class on some biomolecules, so it should be fun. You could still do this for a sugar, and this is an amino acid, the building blocks of proteins. So all of these biomolecules, you can use VSEPR theory to predict their shapes. Okay, well, that's it for now. I will see you later. Take care.